Okay, let's continue on with the second part of Chapter 3. We're still on numerical descriptions of data, but we've got some more information to cover. Okay, next let's look at other ways to view measures of dispersion. First, let's take a look at the empirical rule. Now, the empirical rule is used when a set of data is approximately bell-shaped. And that's when you take your data and you plot it out to a visual representation, such as a histogram. And then we see what shape that data is. If it's a bell shape, then we can use the empirical rule. The empirical rule states that approximately 68% of the data lies within one standard deviation of the mean. So that would mean that 68% of the data in terms of dispersion lies within one standard deviation of the mean. We've learned how to calculate the mean. We've learned how to calculate the standard deviation. It also states that approximately 95% of the data lies within two standard deviations of the mean. So we see that more and more of the overall data values lie within 2 standard deviations of the mean, or 95% of the data. And lastly, we see that approximately 99.7% of the data lies within 3 standard deviations of the mean. So that's almost all of the data can be found within 3 standard deviations of the mean when you have a bell-shaped data set representation. Next, let's take a look at an example using the empirical rule. The average weight of a newborn baby's is bell-shaped with the mean of 3,325 grams and a standard deviation of 571 grams. So we ask, what percentage of newborn babies weigh between 2,183 and 4,467 grams. For a solution, after we plot this data on a histogram, we see that since the data is bell-shaped, we can use the empirical rule. First, we need to know how many standard deviations both values are from the mean. So we do our calculations to find that out. We take the 2,183 and divide it by, subtract it from the 3,325, and that gives us a negative 1,142 divided by our standard deviation of 571, and that gives us a negative 2. Next, we take the 4,467 grams and subtract that once again from the mean of 3,325 grams, and that would give us 1,142 divided by 571, or a positive 2. The data is 2 standard deviations above, that would be the plus 2, and 2 standard deviations below the mean, and that would be the negative 2. So therefore, approximately 95% of the newborn babies weigh between 2,183 and 4,467 grams. Next, let's take a look at Chebyshevs theorem as another measure of dispersion. When the empirical rule cannot be used, Chebyshevs theorem can help to give a minimum estimate, and perhaps the data, once it's plotted using a histogram, isn't in a bell-shaped curve. And so we would turn to Chebyshevs. It can help to give a minimum estimate. So the proportion of data that lie within K, and K is just a symbol, standard deviations of the mean is at least 1 minus 1 divided by K squared, and that's for K is greater than 1. So if we say K equals 2, and you select the value of 2, or the value of K, we would say at least 1 minus 1 divided by 2 squared, which equals 3 divided by 4, which equals 75%. So we know that 75% of the data lies within 2 standard deviations of the mean. And we chose 2 as the measure of standard deviation. And for 2, we have 75% of the data. If we choose a K of 3, we would see that at least 1 minus 1 divided by 3, which is represented by K, squared equals 8 divided by 9, which equals 88.9%. So that we know now that 88.9% of the data lies within 3 standard deviations of the mean. Let's take a look at how we can use Chebyshevs theorem with an example. Suppose that in one small town, average income is $34,200 with the standard deviation of $2,200. So we want to find out what percentage of households earn between $29,800 and $38,600. So let's see how we would find that using Chebyshevs theorem. For our solution, since we do not know if the data is bell-shaped, we cannot use the empirical rule. But we can apply Chebyshevs theorem to find a minimum estimate. First, we need to know how many standard deviations both values are from the mean. So we take our values. We've got $29,800 minus $34,200, and so that would give us a negative $4,400 divided by our standard deviation of $2,200 would give us a negative 2. Then we would take our next set of values, 38,600 minus 34,200 equals 4,400 divided by 2,200, which would give us 2. The data is 2 standard deviations above and 2 below the mean. So if we're using Chebyshevs theorem, we would use a K equal to 2, and we know 2 standard deviations means that 75% of the household incomes lie within this range. Next, let's take a look at measures of relative position. A measure of relative position tells where data values fall within the ordered set. The measures of relative position we calculate, or we will calculate, are the quartiles, percentiles, and standard score. First, let's take a look at quartiles. Quartiles divide a data set into 4 equal parts, or into quarters. Thus, we have quartiles. To find the quartiles of a data set, first we want to find the median, and we know the median is the middle value. and that would be represented by Q2. Next, we want to use the median to divide the data into two groups. For an odd number of data points, include the median in both the upper and the lower halves. For an even number of data points, do not include the median in either half. And step 3, the median of the lower group is Q1 and the median of the upper group is Q3. So let's take a look at how this would be represented. So for our quartiles, we have an example. We've got the data set of 2, 3, 5, 7, 8, 9, 10, 12, and 15. First, we want to find the median or middle value, and we can see that the data value 8 falls directly in the middle of our data set. Now we need to find the first half of data, and we can see the first half of data would be represented by Q1 equals 5. 5 is right there in the middle between 2, 3, 5, 7, and 8. 5 is directly in the middle of the first half of data. Finally, we find the median or middle of the second half of data. So that would be the middle value from 8 to 15. And we see that would be represented by Q3, and that would equal 10. So now we've divided our data set into quartiles. We've got Q2, which is 8, Q1, which is 5, and Q3, which is 10. And that would divide our data set into quartiles or quarters. Now let's take a look at a data set value. This is a little longer data set value. We have 10, 12, 14, 15, 14, 16, 17, 18, 10, 19, 17, and 17. So the first thing we want to do is order the data. And so we'll order it from smallest to largest data values, or ascending order. And once we do that, we can find the middle value, or Q2, to be 15.5. We can find our Q1 to be 13, and our Q3 to be 17. Now to find our Q2, which is directly in the middle of our data set values, we add the two middle values, 16 and 15. So 15 plus 16, and then we divide that by 2, and that gives us 15.5. Next, we can find our first half of our data set values by taking the middle values of 12 and 14, adding those together, dividing them by 2, which would give us a Q1 of 13. And then our last half of our ordered data set value, and we've got the values of 17 right in the middle, and that would represent Q3. Now let's take a look at another data set and find the quartiles. First, we want to order the data, and so we ordered from smallest to largest, 11 to 36. Find our middle value, which would represent Q2, which is 19. Then find our Q1 value of the first half of the data, which would give us 15.5. And then our Q3 value, which would be the middle value in our last half of the data set, which would be 26.5. Now I can see that you're catching on to this, so let's take a look at the 5-number summary. The 5-number summary contains the following values: a minimum value, the first quartile value, or Q1, the median value of Q2, the third quartile value of Q3, and then the maximum value. So that gives us our 5-number summary. So now that we've taken a look at some other measures of relative precision, let's take a look at percentiles. Now percentiles divide the data into 100 equal parts, thus percentiles, or percentages. At the nth percentile, n% of the data lies at or below a given value. So let's take a look at our formula. We'll use the letter L to represent our percentiles equals n, the number of data set values, times p, our percentage, divided by 100, where L equals the location of the data value, P equals the percentile as a whole number, and N equals our sample size, the number of data values. And so now we've got our formula for. Okay, let's continue on with our percentiles. When using this formula to find the location of the percentile's value in the data set, you must make sure to follow these 2 rules. Number 1, if the formula results in a decimal value for L, or location, the location is the next largest integer. Rule number 2, if the formula results in a whole number, the percentile's value is the average of the value in the location and the one in the next largest location. So let's go over those rules one more time. The first rule, if the formula results in a decimal value of L, or location, the location is the next largest integer. Rule number 2, if the formula results in a whole number, the percentile's value is the average of the value in that location and the one in the next largest location. So when calculating the percentile, always round up to the next integer. Okay, now we've got an example for percentiles. What data value lies at the 30th percentile? And we've got columns and rows of data set values. So let's take a look. First, we want to order the data in ascending order. So the smallest value is 11, ascending to the largest value, which is 36. So now we've got our data ordered. Then we would take a look and find out what is the sample size. How many data values do we have there? If we count them, we see that we have 15 data values, so n equals 15. Next, we want to find the 30th percentile, and so that would mean that p equals 30. So using our formula, we would have L equals n times p over 100. So that would be L equals 15 times 30 divided by 100 would give us 4.5. Since L equals 4.5, we'll round up. We've got a decimal, so we want to round up to the next largest number, which is 5. And the value in the 5th position is 16. If we take a look at our ordered data and we count in 5 places, we would have 11, 11, 14, 15, 16. 16 is in our 5th position, so we know now we've found the data value that lies at the 30th percentile, and that would be the number 16. That data value, 16, would lie at the 30th percentile of our data. Next, let's take a look at standard scores. Standard scores are also known as z-scores, and z-scores tell a data value's position in relation to the mean of the data set. The formula that we use to find the standard score is z equals a data value minus the mean divided by the standard deviation. And so we have Greek formulas, Greek symbols in this particular formula, so we know we've got a population formula. But we also have a sample formula. We have z equals a data value minus the mean. We've got the x bar indicating that it's a sample divided by the standard deviation with an s. So we've got this formula for the standard score, or z-scores, for a population and for a sample. Mu equals the population mean, Greek symbol mu. X bar equals the sample mean. Sigma is the population standard deviation, and S is the sample standard deviation. So let's take a look at how we find the standard score using an example. Suppose that the mean on test 1 was 80.1 with the standard deviation of 6.3 points. If a student made a 92.5, what is the student's standard score? First thing we want to take a look at is our mean, which is 80.1. Next, we take a look at our standard deviation, which is 6.3. Next, we take a look at our sample value, which is 92.5. And we find our standard score, or z equals, using our formula, 92.5 minus 80.1 divided by 6.3. So we've got our data value minus the mean divided by the standard deviation. So that gives us a z-score of 1.97. When calculating the standard score, always round to 2 decimal places.